So, first of all, let me tell you a little bit who we are. Okay. So I'm part of the Donosti Advanced Physical Chemistry Lab, the DAPC. It's important here to distinguish from another institution. The DAPC, actually, it's partial in the DIPC and at the University of the Basque Country, and it consists of 4 groups: the theoretical chemistry group, the inorganic photochemistry group, the molecular electronic structure group, and the quantum chemistry development group. And we are all led by the supreme leader, which is Xabier López. And in particular, I'm going to talk about what we do at the quantum chemistry development group, which consists of these people that you can see here, and with whom we work about method development, so development of electronic structure methods, calculation and computation of molecular properties, and also study the problem of electron delocalization. So connected to the problem of method development, one thing I've been working with for a long time is understanding well electron correlation. Actually, the first part of my talk will be about electron correlation. Why do we care about electron correlation, and what do we do with the tools that we develop around electron correlation? And it even connects with molecular properties. When you think about van der Waals interactions are just electron correlation at long distances. So if you can account for those, in a way, you're also accounting for electron correlation. In particular, we are interested in nonlinear optics. We are also interested in vibrational properties, but lately we have put the focus of molecular properties into the computation of nonlinear optical properties. And connected to electron delocalization, we study mostly about aromaticity. For us, electron delocalization is a quantum effect. It's what actually binds molecules with a covalent bond. Means that the electron is not sitting in this atom or the other, it's just delocalized between the 2 atoms. That's what makes the covalent bond. And actually, if you extend the number of atoms involved and you make a ring, the electron delocalization along the ring, sometimes even across the ring, is actually what we chemists call aromaticity. And then when you have such a thing, you induce a magnetic field perpendicular to the field, to the plane of the molecule. And what you get in response is a ring current that you can measure. So this part of my research, which is aromaticity and electron delocalization, I have actually decided not to talk about it today because on the interest of time, I think it would be much more interesting focusing on method development and molecular properties. But if you're interested in this part, please just send me an email, come to me to my office in building number 4, and we can discuss it. So let's start with the first tale that I want to explain you about. That's the electron correlation tale. So this is about how important is measuring electron correlation for us and how we can use to develop new electronic structure. So let's go back like almost 70 years. It was then when Loftin defined electron correlation based on a concept that was already there in the literature for some time, because Wigner and Seitz were studying metallic sodium, and they actually put forward one concept that stayed there forever, which is electron correlation. Electron correlation is actually what is missing from a simple Hartree-Fock picture to actually reach the exact description of the system. Since we are starting from Hartree-Fock, whatever else is missing is what we would call electron correlation. This is kind of broad and a little bit unspecific, and that's why Loftin decided to concentrate on energy and say that actually the electron correlation energy is just the difference between the exact energy and that you can retrieve from a Hartree-Fock picture. Actually, before him, Pines made a definition which is a little bit more convenient for us chemists, which is the following. Instead of measuring correlation as the distance between Hartree-Fock and the exact solution, which most of the times you don't have it, why don't you measure the distance from the starting point, Hartree-Fock, to wherever you are when you are computing a given electronic structure method. So you perform an approximation, you already know you are beyond Hartree-Fock, so let's measure the distance that you walk from Hartree-Fock, and let's call that electron correlation. If you do that, then you have one advantage. You can calculate electron correlation almost all the time. But you're, of course, relying on the premise that the amount of electron correlation that you're retrieving with the system is informative about the total electron correlation that you have in the system, which fortunately turns to be the case in many instances. So electron correlation being important, it starts to be a concept that chemists use all the time. So now if you talk to a chemist, you will need to probably understand some kind of jargon, like, for instance, dynamic and non-dynamic correlation, long-range and short-range correlation, angular, radial. All these kind of things are actually talked about when you try to explain why a method is missing electron correlation. In particular, in this talk, I want to concentrate on two particular kinds of electron correlation. But before I do that, let's try to understand why do we care about electron correlation. So the first thing is the obvious one, it's reliability. So can we trust a given correlation, a given calculation? If we are missing correlation, we cannot trust it. As long as we can retrieve the part of correlation we're interested in principle, we can rely on it. The second one is development of electronic structure methods. So we know how to compute the exact energy of any molecular system. Simply, we cannot do it. And that's why we use some approximate methods that we can actually compute and then obtain some approximations to the exact correlation of the system. If we know what we are missing, which part of correlation, then we can construct methods tailored to recover that part of correlation that we are interested in. And finally, is the predictability. So we want to make sure that we can anticipate which methods can be used. Now, if you try to, let's say, study a given molecular problem, there is a number of methods that you can use. You can use DFT. Even within DFT, you have many approximations. You can use wave function theory. You can study hard-tree fog. You can use perturbation theory. There's all kinds of methods. How do we choose which method do we need to use anytime? If we can predict the kind of correlation that we are missing, then we can make a judicious choice of the method that we want to use. And for us, the most important distinction about correlation is between dynamic and non-dynamic correlation. Dynamic correlation is actually the most typical kind of correlation. It's the one that we always think about. At the hard-tree fog picture, we always say that electrons are actually not well represented because we are underestimating the electron-electron repulsion. So as a result, electrons just get closer together, okay? So if you introduce electron correlation, you introduce dynamic electron correlation, the first effect that you actually correct for is the fact that the electrons should be a little bit farther on average one from the other, okay? This kind of correlation, actually, it's everywhere. It's the kind of correlation that you retrieve, for instance, with perturbation theory or with a method which is called CISD or couplet cluster, if you know these methods in computational chemistry. And it happens, for instance, in the helium dimer. In the helium dimer, what you have is a van der Waals interaction that is long range, but that's dynamic in nature. And usually dynamic correlation, it's actually happens in systems where the hard-tree fog is already quite a good description of what's going on. So we're only missing a little bit of that description, and then we can retrieve it in a relatively simple way from the hard-tree fog picture. That's why they are called single reference methods, because they start from hard-tree fog as a good reference. On the other side, you have non-dynamic correlation, which actually happens whenever we have degeneracies. So in hard-tree fog, you have a number of orbitals, and you put electrons into those orbitals. If at some point you see two orbitals very close in energy, you have to decide which one to put the electrons. That's going to be a system which is going to be plugged with non-dynamic correlation, because you should consider different distributions of the electrons in the orbitals to actually have a fair first description of the system. Okay? And that's why we call them multi-reference methods. You need hard-tree fog, but you need all the determinants as well in your expansion if you want to retrieve this correlation well. That happens whenever you're stretching bonds, when you have two energy levels, one very close to another, or when you have radicals, for instance. So how do we actually try to calculate correlation? What you're seeing here is the measures that we designed over the last years, okay? The idea is relatively simple. What we do is we take these quantities here, which are natural occupations. The natural occupations are the eigenvalues of the density matrix. So you construct the density matrix, and then you have a hard-tree fog picture. The eigenvalues that you get back are actually 1 for occupied orbitals and 0 for virtual orbitals, and there is nothing else. But if you actually make the wave function more sophisticated, this picture breaks. And then those eigenvalues are between 0 and 1. The closer they are to 0 and 1, the closer you are to the Hartree-Fock picture. So you can use these values to measure how much you are deviating. So let's take one example, the one here, which is a one orbital picture. So let's suppose we only have one occupation. If we are close to 0, then it means that we don't have much correlation. So the index that we designed that is called dynamic correlation is going to be very close to 0, is going to deviate a little bit, but then it will go down to 0 when you have occupation of 1/2. So if you're in a situation in which you have actually eigenvalues which are 1/2, it means that two orbitals in a way are sharing one electron. In this situation, what you have is non-dynamic correlation. That's why the quantity in blue have a 0 here, and the one in red, which accounts for non-dynamic correlation, has a maximum, as you can see. So we have these two measures to measure dynamic and non-dynamic correlation. We can make them size intensive. So we just divide by the number of electrons that we have in our system, or we can just take the maximum contribution. So this one is actually quite important for us, because instead of looking at an average, like this quantity, a deviation from the values which are 0 or 1, what we are doing there is taking only the highest deviation. So the orbital that is most different from the Hartree-Fock picture, which is 0 or 1. Okay. So those were the indices that we developed. Now let's suppose that you want to look for electron correlation in some system. You want to know whether that system is electron correlated or not. And you want to say whether you can use a single reference method, like Hartree-Fock, or you need to use multi-reference methods. So if you want to do that, then you can go for shopping at the supermarket of electron correlation measures, and actually you will find that there is 3 main categories. One's based on energy, other based on features of the wave function that you're computing, and the other one based on natural orbitals, which includes some of the ones that I described in the previous slide. If you're actually using the energy, one thing that you can use as a measure of electron correlation would be the percentage of electron correlation. That's an obvious one. How much the energy of correlation weights with respect to the total. You can only focus in the opposite spin correlation, which is usually more important, the same spin correlation. Or you could focus on the triple contributions to several quantities. The wave function methods actually I will not explain them all because it will take some time, but let's say that all of them will probably go to numbers very close to 0 when you are going to the Hartree-Fock picture, and you will deviate more and more and more as you actually introduce more electron correlation in your system. And the ones about natural orbitals that we care about, I already explained in the previous slide. So what we did with Chiang during his PhD thesis is actually find correlations between these different indicators. He wanted to know how different one correlation is from the other, one correlation measure from the other. We wanted to know whether we could use any of these correlation indicators or others were best suited for this work. So we just did this Pearson coefficient matrix. We look at the regime very close to small electron correlation, where we find more, let's say, agreement between the quantities. And then we plot these coefficients to see the agreements. And what we find is the following. The only dynamic correlation index that we are considering actually doesn't correlate very well with the other indices, which are non-dynamic correlated. This one is an exception for reasons I will explain later on. Okay? So it means that dynamic and non-dynamic correlation are well separated one from the other according to this correlation matrix. Those are intensive correlation measures and are fairly correlated between them, but not too much. And they are not so well correlated with the other ones that are called maximum indicators. Those, what they do is they measure the most correlated part of the molecule. So we're not taking an average picture, we're just picking up the most correlated part of the molecule. And for those, we see that almost all of them show very high correlation among them. So it means that it doesn't really matter pretty much which of these measures you use, you are going to get the same answer. But this is not the case if you use wave function quantities or energy-based quantities. So they are measuring something slightly different. And that's when we said, okay, we can simplify a little bit. We can just retain those correlation measures that are distinctive between them. But then which one do we trust the most? So what we did next is we tried to distinguish between these different indicators by doing the following. We measure we were looking for the following qualities in our correlation indicators. If you wanted a correlation measure, so a value, let's say 0.4, 0.5, telling how much correlation we have, then we look for quantities that provide a number, and that could be size intensive. So we could compare molecules of different sizes, okay? But if you want a correlation diagnostic, so a quantity that tells us this molecule is single reference, you don't have to worry, you can use Hartree-Fock or even DFT, or this molecule is multi-reference, you need some more sophisticated methods, then we just need a quantity that actually says yes or no. It must be also size intensive, you can use it among different molecules of different sizes, but it should measure the worst part of the molecule. Because if we have only a very little, teeny tiny part of the molecule, which is multi-reference, we do need a multi-reference method, even if the molecule is so much larger. So that condition actually is what separates the correlation diagnostic from the correlation measures. And what we did next is we designed a system, a hypothetical system, in which we have the oxygen molecule stretched. So we are inducing non-dynamic correlation and multi-reference character in our molecule. And we put next to it different molecules, which are just single reference. This is nitrogen molecule in its ground state. It's a molecule you can calculate simply with almost any single method that you want. By increasing the size of the molecule, we are making the problem bigger and bigger and bigger, but the part we really need to focus in is always the same. So we expect the different correlation indicators to actually have a very similar value all across the spectrum of molecules that we are studying. And what we see is that the energy-based indicators, not only these ones, the other ones that I'm not showing as well, are failing to actually attain this condition. This one is actually also another energy-based. And the only ones that can actually succeed in this test are the IND max, which is that maximum deviation of the occupation between 0 and 1. And then one index, which is called D1. I don't know if you're familiar with those. It's a typical test that is used for Capet cluster. And what it's measuring is the role of single excitations on the expansions. So there is a theorem due to Tholes who actually says that you can actually freely rotate the orbitals in your system, and you could obtain a method in which single excitations account nothing. So it means that a method like D1 is a little bit dangerous to be used in practice, and we do not recommend it. So at the end of the day, we are left with one reliable indicator to account for multi-correlation, for multi-reference effects. And that's the one that we are staying with and the one that we are using for further applications. So let me show you one of those things that we are trying to do right now. This is an ongoing work that is being done by Markel, mostly, in which we try to extend all that we did so far using these correlation indicators to DFT. Because what we did so far, it was based on wave function methods, because we need natural orbital occupances that were different from 0 and 1, and you cannot get those from DFT. Doesn't matter which approximation you use. So in practice, what we did next is trying to retrieve that information using a support vector machine method, in which we are using the Consham energies from DFT as an input. And what we are trying to predict is whether our molecule is single reference or multi-reference using the IND max method that I described earlier. So what Markel did is using two different sets, one training set and one large test set. And he found that actually we could correlate against IND max pretty well with the machine learning model and get an accuracy of 92%. So it means that 92% of the molecules are well characterized. However, we do care about a particular kind of molecules that are not well characterized. And those are the ones that are multi-reference but they can be mistaken as a single reference molecule. Because if we cannot discard those which are multi-reference from our set, then we cannot use that set, for instance, to compute anything at the DFT level. We care much more about those rather than to get off the set molecules that are not multi-reference, but they are wrongly characterized as multi-reference. And that's what we measure through the recall, which is 99%. So we can leave only 1% of the molecules being wrong in our set by using this machine learning model. And that's what we are still kind of, let's say, polishing with Markel, but we hope to publish this one soon. And to end up this first tale, let me tell you about how we can use this to design electronic structure methods. So what we do is actually, we start from the so-called Moller-Plesset second-order perturbation theory. The Moller-Plesset perturbation theory is one of the simplest methods you have in quantum mechanics. You start with a Hartree-Fock description, and then what you do is a perturbation theory in which your perturbation parameter is the interaction between the electrons. If you do it, you will get an expansion at the energy level and the wave function level, and if you cut it at the second level, you get the simplest perturbation expansion, which is meaningful, which is the second-order Moller-Plesset perturbation theory, or MP2. MP2 has a problem, which is it tends to underestimate the opposite spin correlation. There is a reason for that. The Hartree-Fock wave function actually already contains some correlation of the same spin electrons. And that's because you are constructing a Slater determinant, which is antisymmetric by nature. So in a way, the same spin electrons are already slightly seeing each other. So when you are starting from Hartree-Fock, the same spin interaction is ahead, and the opposite spin interaction is not so well accounted for. That's why Grimme, some 20 years ago, suggested that maybe we could separate the correlation that MP2 gives you into the same spin and opposite spin, and then use different weightings for those parts. He just used an empirical parameters that work well to reproduce some reaction energies, and he got numbers of 1/3 for the same spin and 1.2 for the opposite spin. However, as research evolved in this field, they realized that actually the optimal coefficients are system dependent. So if you fix them, actually you are biasing towards the systems they use for the calibration. So it would be nice if you could actually dynamically change these coefficients depending on the system that you have. So what we thought is that we could use electron correlation for that, because the same spin correlation is more connected to the dynamic correlation, and the opposite spin correlation is more connected to the non-dynamic correlation. This is a huge assumption, okay? Correlation is important, non-dynamic and dynamic, regardless of the spin types that you have. But what we have seen is that actually the opposite spin correlation is far more important in non-dynamic correlation than it is in the same spin correlation. And since we are going to take a percentage of that thing, if this is 40, that's going to be 60. So in a way, you are controlling one coefficient with the other, okay? Because they fulfill this obvious sum rule. So what we did then is we applied this, let's say, this parameterization using our correlation indicators, and then computed in a small collection of molecules. And what we found is that with respect to MP2, we could reduce the error up to 1 kilocale per mole in the test set. We are now still working on this. We have a larger training set to see how far we can go, because of course, the actual value that we're going to obtain is not going to be as good as 1 kilocale per mole. This is just the training, but it's going to be some number, not so much larger than this one. So that was the first tale that I want to tell you about. Let's start with the second one. This is a tale of serendipity. So something that we found when we were not looking for that. So it's about how, studying nonlinear optical properties, we found an important deficiency that density functional approximations have, and how we can actually fix it. So to do that, let me start introducing a little bit this research field. What we care about here is light-matter interactions. The idea is that we have piece of matter, a molecule, and there is an external radiation. Whatever radiation we are having, we are assuming that the frequency is low enough so that the molecule, let's say, sees the radiation as uniform, let's say, within time. So it means that we can actually treat the radiation classically. So we don't care so much about the radiation, we care much more about the molecule, which we are going to treat with quantum methods. And what we want to know is actually how the dipole moment of that molecule is going to change depending on the electric field that represents the external radiation that we are applying on our molecule. We simply do a Taylor series expansion, and what we have is the static dipole moment, and then the response parameters or the response functions. The linear response is the polarizability, the nonlinear response are the beta and the gamma, which are the first and the second nonlinear response. Okay. So this is the idea of what we want to study. In practice, what we actually do is we use a very intense light source, usually a laser, that irradiates into the sample. And then by having so many photons hitting the molecule at the same time, eventually 2 photons had hit the molecule simultaneously. When that happens, those photons can be like virtually absorbed. This is not a state, let's say a stationary state. This is just a virtual state that we made up to explain this phenomena. And then they can be scattered into a radiation which has twice the frequency of the incident one if the 2 photons had the same frequency. They had different frequencies, you would just sum the frequencies and get light out of this with a different frequency. That's the way, for instance, you could take a laser with a given frequency, construct another laser with a higher frequency, okay? So in practice, this kind of phenomena in which various photons are interacting at the same time in the molecule are called nonlinear optical phenomena. There is many different kinds that you can have. Here there is a small summary. There is the sum frequency generation. The one that I described above is the second harmonic generation. You have the electro-optical Kerr effect. There are many, let's say, different methods. In practice, what this is useful for is for spectroscopic techniques, because since it depends on the material whether 2 photons will actually interact to give another photon of higher frequency, you can use it to characterize different kinds of materials, okay? So this kind of research line is the one that we carry out in collaboration with a few people from the University of Bordeaux, Frédéric Castet, from the University of Girona, Josep Maria Luis, from the Technical University of Wrocław, Robert Salesny, and from here, Eli Rezabal, with whom we lately are studying the nonlinear optical properties in ionic liquids. When we were performing some years ago, some 5 years ago, with Josep Maria and Robert, some calculations, we found the following thing. What we were doing is trying to see these hyperpolarizabilities and polarizabilities that we obtain applying an external electric field on molecules when we want to take into account what is called a nuclear relaxation. So what I explained is what they call the electronic part of the nonlinear optical properties. But if you take into account that your molecule in practice actually vibrates and it has to, let's say, relax, you have to include a nuclear relaxation term, which accounts for this nuclear motion of the molecule. If you include those, then you can account for the full nonlinear optical response. Otherwise, you only have the electric one. In this case, we're studying hydrogen-bonded complexes, which has this low vibrational mode, which is important and increases a lot the response from the nuclear point of view. And what we did is we calculated this alpha, beta, and gamma, this linear response, the electronic, and the nuclear relaxation terms. And you can see here is just the error committed against some high reference calculation. What we see is that in general, things are performing quite well, but then we saw that the nuclear relaxation term for a few functionals has actually very large errors. Those errors are actually off the scale. Here you can see 100 is a red color, but those numbers are actually 1,000%. So we had 1,000% error on the response properties of hydrogen-bonded complexes. And we always say DFT is never right, but it's never so wrong, and definitely not that wrong. So it looked like something was going on here, and we wanted to look into it a little bit more in detail. So we just went inside these equations that we need to compute the nuclear relaxation terms, and we realized that actually the third and the fourth order energy derivatives with respect to the nuclear displacements were wrong. And we're wrong for about the same quantity that you are being wrong in the property that you want to calculate. And then we decided, okay, we can stop here. We just report that this is a problem, or we can try to understand why is it so? Why do we have such large errors in these energy derivatives? Since this is something that is happening when we move the nuclei, why don't we plot these energy derivatives along the nuclear displacement?
A very short question.
Yeah.
Here, density functional theory is time-dependent density functional theory or static density functional theory?
It's time dependent.
Time-dependent.
Yes, it's time dependent. So what we did is we plot the energy derivative with respect to the displacement, okay, for different molecules. The second order derivative, third and fourth order for different functionals. Those are the functionals that we already saw they were failing. And we plotted also Capet cluster, which is a very good reference in quantum chemistry, to see if there were deviations. And what we saw was quite striking, because you can see that there is this kind of large deviations, these oscillations. We don't know how these things look like. I think never anybody plotted these energy derivative profiles for these particular molecules. So they could be oscillating, but it was kind of weird, especially since Capet cluster is not oscillating. And the higher the derivative, the more oscillations that you see. The first thing that we thought is, okay, maybe we're doing wrong the energy derivatives. Maybe there is a numerical derivative error. We discarded that after doing some of those analytically, okay? And then we said, okay, let's study why this is happening. Let's change the grid. The grid is actually the numerical grid that you use to compute the energies at the DFT level. I will come back to the grids later on. And what we saw is that if we increase the grid, so the accuracy of this numerical integration, we see that things get a little bit better. You can see here that the largest grid, which is in the green line, is actually absent in this one, and it gets a little bit larger in these two functionals. But if you use lower grids, you see the oscillation. So it's seeing a property which was grid dependent. So the next thing that we did is trying to diagnose this. Sebastian, together with Jose Maria, Eloy, and also Robert, we decided to study this carefully. We had studied only a few functionals, so we took a much larger collection of functionals. We compute other properties, well, not only energy derivatives, also compute dipole moment derivatives and polarizability derivatives. And then we try to study molecules that were not covalently bonded, because so far we had seen this in hydrogen bonded complexes and also in noble gases. So we wanted to study something else. We studied here halogen molecules, but then it's not part of this study, but we study another molecules that were not, let's say, covalently bonded to see if that was an issue.
I'm very sorry, but here time-dependent density functional theory is adiabatic DFT or dynamic DFT?
It's adiabatic.
Adiabatic.
It's adiabatic, yes.
Yeah. So one source of errors can come from here, right?
Yes, if I make a spoiler, I would say no, but let's say at this point, you could think that that could be a case. But I'm making a spoiler here, you will see that that's not going to be the reason why is it so. If you give me a little time, you will see. So what I'm showing here are the results that we got for different functionals, summarized. So let me explain a little bit what you are watching now. What you are seeing is energy derivatives, dipole moment derivatives, and polarizability derivative for three different sets of molecules: hydrogen, halogen bonded, and van der Waals complexes. And the number that here is represented, it actually corresponds to the highest order derivative that we can calculate accurately. It means that we are going to have at most 10% of those oscillations that you are seeing. So we quantify those oscillations, and the amplitude gives an idea of how much they oscillate. If they do not oscillate that much, we can trust them. And then, for instance, here we are saying that up to the fourth order derivative, which was the higher we could test, the functional B half and half is actually giving a right answer. But when it comes, for instance, to compounds C, which are the van der Waals ones, we could only actually calculate up to third order. The fourth order derivative contain errors higher than this 10%. And then we make what we call a safety ladder. This is not about precision. The quantity could be wrong altogether. We are only counting whether those oscillations are showing up or not. And what we see is that just these two functionals can perform almost completely well, except for the fourth order derivative of van der Waals complexes. Those three in what we call rank 2 are limited to harmonic frequencies in the case of van der Waals. You can only calculate up to second derivatives. And on rank 3 is where trouble starts, because we cannot calculate any van der Waals complexes. We can only calculate hydrogen and halogen bonding. The fourth rank, it's a no-no, because you can only calculate harmonic frequencies for the halogen and hydrogen bonded molecules. And the rank 5 is just functions that they are useless, completely useless to these kind of things, because sometimes you cannot even get the first derivative correctly. Okay, that's what kind of striking when we found it, because it really tells that if you're going to use these kind of functionals to perform vibrational calculations of vibrational properties, or whatever thing that involves moving nuclei, you should be mindful that actually you're committing error on energies derivatives, and those can propagate to the properties that involve those derivatives. So the conclusions were that we had to use a pretty large grid that was not usually used in the calculation so far, that they were very sensitive to this numerical grid, which is involved in this conclusion, that a few family of very popular functionals, at least in the quantum chemistry community, should not be used at all, and that some functionals are robust, but some of them are pretty old. This is a functional from the 90s. I mean, almost nobody is using this functional for anything nowadays because the precision of this functional to calculate properties is rather low. So it left only a few functionals that could be robustly used for this kind of calculations. We also identified that low frequency mode molecules are very prone to this problem. And the thing is, there are almost a zillion collection of molecules that have a low frequency mode. It's not only non-covalently bonded molecules. For instance, in benzene, which is a pretty innocent molecule by itself, there is a breathing mode in which hydrogens move like this, in which the fourth order derivative of the energy has still large errors with many popular functions. Why this is not detected so far, or was not detected so far? Because in practice, you are rarely using third and fourth order derivatives. You want frequencies to characterize the potentialized surface of your molecule, but the fourth and the third order derivative are needed only if you want to calculate infrared and Raman spectra, especially if you need intensities of those spectra, or if you are doing molecular properties that involve correction of the vibrational displacement, and then you will need higher order derivatives of the energies. Essentially things that little by little we are using in the DFT community, but so far they were not used so much. Plus, these errors could be easily disguised as performance error of the functional. Maybe we were seeing oscillations were there, they were causing problems, and people assumed that the functional was wrongly accounting for it, rather than being a problem of the grid. Okay. So the second part of this talk actually connects the molecular properties part with the method development, because we wanted to understand well why some functionals fail more than the others. And we attempted to do this part with Andrei Paula, who is sitting over there. And of course, the first thing that we tried to examine on the energy expression of the density functional approximation was the only part that we need to integrate, because this is a grid-dependent property. And that's the so-called exchange correlation energy density. Okay, that's where we have this numerical precision leak in the integration, which we believe cause all these problems. Since to calculate this, you have to perform this numerical integration, we said, okay, why don't we look at the quantity that we need to integrate? That's what characterizes each function, or maybe that's where the problem would be. So we did the derivative under the integration, and we simply examine now the derivative of the integrand that once integrated will give the property that we are looking for, and we know it's making all kinds of trouble. So what Andrei did is he plotted these quantities, so the integrand, and he found this graph that you can see here. What is this graph? So this is the quantity we need to integrate to get back that energy piece, actually the energy derivative of that piece. But we are focusing on a very small part of that, let's say, large numerical space that we need to integrate. We are only looking, and this is the argon-argon molecule, at the middle between the two argon atoms. That's what people call the bond critical point, is where the density actually has a minimum. If we look at that point, we would have expected that things are essentially absent there, because this is an argon-argon interaction. There are two closed shells. There is no much density in between the two atoms. And instead, what we found, it's a small but non-negligible oscillation. Much nicer oscillations than we had before for the whole property, but there is an oscillation over there. And then we compare this oscillation that we see for some of the world's functionals against a functional, LDA, which is the simplest one you can have, and see that actually the LDA does not oscillate. And then we said, okay, so what's going on here? Is it a physical thing and simply LDA is not good enough to reproduce these features? Or this is an artifact and LDA is kind of giving us the right answer about this region? Think that energy-wise, this region is completely irrelevant because there is almost nothing over there. But in practice, when you're doing energy derivatives, that starts to be more important than it would be for the energy itself. So a little bit of language here. I'm going to call these oscillations either micro oscillations or integrant oscillations. Well, the others that we had on the property, those that were a little bit more nasty, I'm going to call property oscillations. So what Andre did, and this is a graph that has only a few days, he plotted the maximum amplitude of the oscillations of the property against those of the integrant. And I think it's pretty obvious that one thing is connected to the other. We didn't expect, let's say, this linear correlation. We expected some correlation, but it was actually very nice correlation. It breaks if you start, let's say, studying other molecules. It's never such a nice linear, but I use this one for the presentations. But the point is that we have a clear connection between the oscillations that we are seeing at the integrant level and the ones at the property. And actually, if we get rid of the oscillations that we are seeing, like we saw in the previous slide, the property does not oscillate anymore. So something is wrong on the functional itself, because we are plotting the integrand. We have no integration yet. There is no grid involved whatsoever. So it looks like something is wrong on the functional itself, and it manifests if you lose a small grid. So then we look into one functional expression itself, the B97 case. This is the typical expression of a correlation, a GGA functional. So this is the exchange, the same spin and the opposite spin correlation, has some parameters that depend at the end of the day on the reduced density gradient. And there is some mapping between the reduced density gradient, which takes value between 0 and infinity, and these U polynomials, which take value between 0 and 1. This is the Lorentz transformation to get things numerically under control, so to speak. And this, back in the day, in 1997, it was actually designed with these particular parameters. Those were obtained for some particular correlation energies of the helium atom and the neon atom. And the one thing that we saw is that actually, strangely, one of the parameters is much larger than the rest. The first obvious thing to try is, let's make that smaller. Let's see what happens. And what we see here is the oscillations now of the property and how they change when we just tweak the functional and make this parameter small, and simply eventually they disappear. Of course, these functionals are not going to be competitive because we just took a functional and changed a parameter out of the blue without caring about whether energies are going to be good or not. That's why later on, Andre did some calibration. So we didn't change things, let's say, we didn't just change one parameter. We start, let's say, optimizing those parameters to get better energies. And what we obtain is what you can see there at the bottom. We can construct a new functional which more or less behaves very similar to the original functional and doesn't have these oscillations at all. So it means there is a way of actually getting rid of these oscillations altogether. B97, it's not, let's say, a very popular functional, but it's the ingredient of one of the most popular functions in quantum chemistry, which is the WB97XD, designed by Martin Head Gordon and used, I don't know, zillion times so far in quantum chemistry. And what Andrei is finishing doing is actually repeating this exercise in that very functional. And so far, the results that we have are promising. We can actually redo that functional so that it's good for vibrational properties and still retains the performance for which the functional was designed for. So I think I have convinced you that it's actually the density functional itself, the structure of the functional, that is responsible for the spurious oscillations. We saw that linear correlation connecting one thing to the other. It occurs in the vicinity of the ring critical point. So it occurs whenever we are looking at places where the derivative of the energy with respect to the position is zero. And that happens between two atoms. It happens also at the nuclei, but in the nuclei it's not that important, and in other regions of the molecule. And that we can construct new density functional approximations that are free of these oscillations. So connected to DFT, let me tell you that in 2 years, a little bit less than 2 years, we'll have the DFT conference here organized in Girona, in Donostia, in Donostia. And you are very welcome to attend. It will be around those dates in August 2026. And finally, let me acknowledge all the people that actually helped me through this. First to Jesus, who was the one who invited to come here to Donostia like 10 years ago. I started working with him in many different things, also with Xabier and some other people. I have not shown some of these works because I prefer to concentrate on the last ones that we are working. I definitely need to acknowledge the number of PhD students that actually were involved in these works and I had the privilege to work with, and also the number of postdocs, and of course the current members of the Quantum Chemistry Development Group and the Donostia Advanced Physical Chemistry Lab. Thank you very much for your attention.
So we open the room for discussion, comments. Roberto?
Yes. Thank you for the talk. I have a question. I've been working in Raman, and I asked him for advice. Considering that all the error in the derivatives affects the oscillation and other properties, do you recommend, for instance, computing the frequencies with one functional and intensities, for instance, infrared Raman with another functional? How to deal with this problem?
Okay. I did that once back in the day when I was a postdoc in Denmark and I was working on vibrational properties. And I remember presenting exactly that kind of Frankenstein into a conference. And some people complained to me that that was kind of, let's say, not the proper way to do things. That being said, my limited experience, because I work on that field for 2 years and only that, is that actually you could do this kind of mixtures and things are going to work more or less fine. So you could calculate frequencies with one and intensities with the other, if all that you want is represent the spectrum at the end of the day. So I think it's not such a bad idea. People are actually doing much worse than that. I can tell you later on, but you can construct PES, actually mixing different methods altogether at different levels of couplings between the normal modes and reproduce a spectra, which is actually much better than with any of the methods separately.
Sorry for returning to my previous question. By using a diabetic TD-DFT, you are seemingly dropping out the whole world of effects. You use a diabetic TD-DFT to handle dynamic properties, right?
Mm-hmm.
Like nonlinear optics and so on. So I don't think this is a minor problem. Yeah, for example, you drop out exciton and many other friction. I mean, not the whole friction, but viscosity and so on. What do you think about this?
So I should first say that when I said to you that those calculations were done with time-dependent DFT, that was correct, but there is another way around it. we don't have to use time-dependent DFT at all. Actually, if you are computing just the static properties, as we were doing in this work, okay, because there were static properties, you can just apply an electric field with and without the electric field and do energy, and you find the differences, you get the answer back. So you don't,
I don't argue that you should use time-dependent, of course, but you don't account for dynamic exchange and correlation, yeah? You do not.
no, but let's say, how to put it, for the problem that we are showing, okay, it doesn't really matter if we use these or more sophisticated methods, because actually for computing the polarizabilities for the second harmonic generation, as far as I know, you can get pretty accurate results using this kind of, let's say, approximation at the DFT level. But we compare it against wave function methods. We actually have a completely separate work that I couldn't put it here, in which we benchmark the density functional approximations against wave function methods like Capet cluster and so on. And we get that on the general picture, you get the same answer for both things for the problems that we are dealing with. But I do not deny that depending which problems you want to work with, then DFT would be essentially not sufficient. Actually, you have seen that for some of the molecules that I'm not showing, for which DFT does not include enough correlation into the system to account well for the response of the property.
DFT is sufficient, but it should be non-local. Exchange correlation should be non-local in time, which is the dynamic exchange correlation.
Yeah, but in practice, let's say we are not using it like that, and that's why it's not sufficient. So I'm talking about the approximations, not the theory.
What is not sufficient? Are you asserting that TD-DFT in its exact form would not be sufficient for solving this problem?
No, it could be. It could be.
It would be. Yes.
Yeah. I'm distinguishing between the theory and the approximations. So on the theory, you're right. On the approximations is where I said that, yeah, that's.
But this particular approximation includes neglecting dynamic properties. Is it correct? Dynamic exchange and correlation.
Yes, dynamic exchange and correlation, yes.
Usually it's a rather rude approximation.
It might be for the things you're working with, but for those, we compare against wave function methods in which you are ignoring none of those things, and you do get the answer. I would say you get the same order, about 80%, maybe there is 20% error, 10% error, but those are not, let's say, errors people would care about for the response properties, because you usually measure them by the order of magnitude. So you want to know if it's 10 to the third or 10 to the fourth. You don't care so much about 5% or 6% as you would care for the energy.
Okay,
for this kind of applications.
Yes, thank you. I now understand what you are doing. Yeah. I'm not convinced that this is the right thing to do, but
in general, I'm sure it's not.
A different question. Okay, thank you very much.
Yeah, I'm starting trying to understand the problem. So can you show again this plot with for the argon? I think it was an argon molecule, right?
Yes.
So what are you showing there? So what is the x-axis there?
The x-axis is the position in the space.
The position of the space of
argon 2. So I'm zooming around the neighborhood of the minimum between the two argon atoms. So that's, let's say, the 0 would be around the midpoint, and those is just atomic unit displacements with respect to that point. So you have to integrate these and everything else that I'm not showing in the three-dimensional space to get back the exchange correlation energy density derivative.
Yeah, and you are then plotting these derivatives of the same correlation density, energy density. Okay, and and then so you focus in this B97 functional, which I don't really know very well how it's constructed, but then you were changing this parameter, but this parameter seemed to be multiplying something which was an LDA at the end of the day, LDA related. Yes.
Let's say
I'm wrong.
The energy just contains the LDA part and then enhancement. That's the typical shape of a GGA. So you just improve over LDA with this function, which is, of course, position dependent. And this function is actually constructed as an expansion of these U functions, which are a transformation of the reduced density gradient, a Lorentz transformation of a reduced density gradient so that it scales between 0 and 1. Okay. And then the parameter that enters this scaling on the same spin case is the one that is actually, let's say, different from the rest. But how this was constructed? So these were fixed by Axel Becker back in the day. He just took the energy of correlation energy of neon and correlation energy of helium, and he fixed those values. And then he took the typical set of atomization energies that he had, and then he forced those C's here to actually reproduce the best possible those energies they had in the set.
Okay, so actually they are multiplying gradients of the density.
Yeah.
Okay, so now I understand a bit more. Okay, because I was a bit puzzled because somehow I thought looking at some of the formulas that it was more like multiplying something which was basically LDA, and I was a bit puzzled that this would give rise to oscillations.
No, LDA doesn't at all.
Anyway, so related to this, I mean, I'm sure you are aware of this, of course, but it is kind of well known that when you work with DGAs, you use these bare formulas, let's say, and you are using some kind of grid in real space, which I'm not sure if this is the case in this particular calculation. You have to avoid using the gradients, but actually you can rely on formulations where you are actually using just the point where you compute the density and using directly like, I mean, at the end of the day, this is where you're computing your density. You don't have access to derivatives. So you can go to formulations in which you are using just this information, these points. And that's the only way to get consistent derivatives in numerical calculations. And I know this exists for many functionals. Maybe for this it's really a challenge because of the particular way they are constructed. But I mean, this is sort of well known to be an issue. But I'm sure you're aware of that. Just to point it out.
The thing is, let's say, if you change the way in which you perform the numerical integration and you get it more accurate, you're going to get the right result eventually, because you have seen molecules for which you do a very, in our opinion, very accurate numerical integration, like 20-fold the size of a regular grid, and still you don't get the right answer. But if you solve things by doing a better numerical integration, you are kind of sweeping the problem under the carpet. Because what we believe is happening here, it's due to the shape of the function itself. So the grid problem is only revealing the inherent problem in the functional expression, which is wrong altogether. And it never manifests because nobody ever cared so far or so much about energy derivatives. But if they would have seen this. And actually, this was reported in Argon 2. I'd say that I'm talking about at the beginning of the 2000s, there was a work in which they found that the potential ionized surface of Argon 2 was oscillating with DFT, with some functionals, with I think it was VSXC and some other functionals. And they were trying to understand why. And the reason is actually similar to the one that we are finding here, but for meta GGAs, not for, let's say, GGAs. And they could solve that, and the problem was kind of solved by increasing the grids. From them on, people, let's say, try to use larger grids, and then the oscillations kind of disappear. But that was, again, I think, just hiding the problem, because there is a way of getting rid of the wrong behavior of the functional expression itself, and a right way to construct it, so that you don't have to care so much about the numerical integration grid later on.
Well, yeah, to me, the fact that you can somehow cure the problem increasing the grid points up to a mostly numerical nature of the problem, which is, from my point of view, a little bit different from whether the functionality is reasonable or not from a physical point of view. But okay, I mean, that's, you are the one working on this, so this is like sort of vision, but I'm perfectly willing to accept that this is not the case. But in any case, and this is not this problem, of course, but some related problems, if you want to say it this way, have been observed for many years, and one of the cues is to try to do consistent derivatives with the numerical way you are computing the energy. And that's, so they are like, GGAs are an issue. I mean, they are very difficult to treat and numerical. in some cases. And
They are, but how to put it? If we can construct ones that are that they don't have the problem on the first place, wouldn't it be better? Because it's not only that we are solving the problem, it's also that we are seeing, comparing to references, that those oscillations on the interior shouldn't be there at all. So we are removing something that is unphysical and might cause problems in something else later on. We just don't know how it causes problems. We just saw it in this very particular case. But having these oscillations here, this is not physical at all. So you can live with that, because what happens if you because here I think it's pretty obvious. If you put enough points around all this curve, eventually you will integrate this well, because what will happen? This will compensate this will compensate this partially. And so it happens with the rest. Maybe here is not so obvious, but I can tell you that this area here and these two areas are similar. So if you integrate well, essentially you are removing the problem by compensating very well what's going on. But if you don't have enough dense grid, then you put 1 point here, 1 point there, and then the iteration is wrong. But if those things shouldn't be there in the first place, I think there is a much cleaner way, just designing functionals that don't have that in the first place. But it's my point of view.
thank you. That's a nice explanation.
Okay, I think Edu will be very happy to discuss with anyone in his office or at 11 o'clock in the coffee, but I think we ran out of time. So please join me thanking again, Edu.